So in this video, I'm going to talk about several special types of series. And the first one I'm going to talk about is called the Harmonic Series. Now, the Harmonic Series is special of these series that I'm going to talk about now because it's the only one that specifically refers to one exact specific series. All of these others are more like families of series where there are multiple different types within that little cluster or under that nomenclature. However, the harmonic series, there's really only one series that fits the bill, and it's the series from n equals 1 to infinity of 1 over n. Now, the way that'll appear is the number 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, and it keeps on going from there. Now, this is special as well for other reasons, like it's very commonly discussed when you talk about things like harmony in music for songs or for strings of an instrument or melodies or anything like that. So this series itself has been studied for a very long time, and its uses have been kind of elaborated over the years. And in fact, this proof that I'm getting ready to show you actually originated several hundred years ago in France by a French mathematician. And so the first thing I want to do is I'm going to start with this harmonic series that I want to figure out whether it converges or diverges. And so we have this series from 1, 1/2, 1/3, 1/4, 1/5. And I'm going to keep going. We'll put it out to 1/6, 1/7, 1/8, and I'll stop at 1/9 just for clarity's sake. Okay, and what I'm going to do is I'm going to compare this to a slightly different function, slightly different series, excuse me, that's a slightly smaller. And so all I'm going to do is I'm going to take each one of these harmonic series terms, and I'm going to find the value of, or the power of 1/2 that's less than or equal to it. So what I mean by that is the first term is actually going to be a 1 because that's 1/2 to the 0. The next term is going to be just regular 1/2 because that's 1/2 to the first. Now, with the 1/3, that's not a power of 1/2. The power of 1/2 that's less than or equal to that, the closest to it is 1/4 because that's 1/2 squared. And for 1/4, I'll still use that 1/4 because, again, it's a power of 1/2. For the next few, the 1/5 is not a power of 1/2. The closest one to it that's less than or equal to it is 1/8. And so same thing with 1/6, 1/7, and 1/8. And the next thing we would go to after that would be 1/16 because that's the next power of 1/2 after that. And hopefully you guys are picking up on the fact that it starts off with 1 and then 1/2 and then 2/4, which is 1/2, and then 4/8, which is 1/2. And the next one would have 8/16, which would also be a 1/2. And the thing to notice here is that as I continue to add more and more numbers here, as I continue to extend this series out toward infinity, what happens is I'm continuing to add 1/2. And so the limit of this sequence as it goes to infinity is actually 1/2. So this is going to be a divergent series because I just keep adding 1/2 over and over and over and over again. So this series, this comparison series, is divergent or diverges. And so because this is slightly smaller than the harmonic series is also going to diverge. And the reason that is again, in this case, what we found is a smaller series that diverges. So the bigger series should also diverge. So the harmonic series always diverges. And we just did this by the direct comparison test. I compared it to a nice, simpler function that worked out nicely. And we said, again, the smaller function diverges, so the bigger function diverges. Now that we've talked about the harmonic series, I'm going to move on to a related series called the p-series. Now, the p-series looks very, very similar to the harmonic series. In fact, the harmonic series is a special case of the p-series because the p-series is 1 over n to the p, where p is an exponent, it's a power. And so the harmonic series actually occurs when p equals 1. Now I'm going to go ahead and just write a couple of terms out. So the first one would be just 1, and then it'd be 1 over 2 to the p, plus 1 over 3 to the p, plus 1 over 4 to the p. I think you guys are getting the idea. With this, we typically expect p to be a positive value. Since it is in the denominator, that's typically what we want, is that p is positive, as in it's greater than 0. But anything other than that is acceptable, so any positive number works. Now, I do want to prove a fact about the p-series, and so what I am going to do is I am going to start with this p-series. So the summation from n equals 1 to infinity of 1 over n to the p. And what I'm going to do is I'm going to apply the integral test to this. Now, if you recall, the integral test says that I can take my infinite series, this summation of n equals 1 to infinity of 1 over n to the p, and I can compare that to the improper integral from 1 to infinity of 1 over x to the p dx. So I can just compare my infinite series directly to an improper integral. Now, hopefully you remember from doing improper integrals that this p integral is what it's called, has a couple of special properties when we go from a number to infinity. Specifically that this comparison series, this integral here that we're going to use, actually does converge, specifically when p is greater than 1. And what it actually converges to, and I want to make sure I write this down, it converges to the first number, or that base. In this case, it would be a 1. So it's 1, or a to the 1 minus p, so whatever that exponent is, over 1 minus p. Now, it doesn't really matter what this converges to, because the series is going to be slightly different. The series doesn't have all of those continuous values like the integral does, but it's nice to know, it's nice to be reminded of what that integral does. But so since the integral converges, then the p-series should also converge when p is greater than 1. Again, not going to necessarily be the same answer. And that means that when p is less than or equal to 1, we should diverge. And again, we use the integral test to show that. I do have a couple of examples for you that I wanted to show you, so let me go ahead and flip over to those. Again, remember, this is the important part. It will converge when p is greater than 1, and it will diverge if p is less than or equal to 1. Okay, so on my p series, the first one that I have, the first example, is the infinite series, n equals 1 to infinity of 3 over n squared. Now, the first thing that's really important here to do is to go ahead and take that 3 and move it on the outside of the summation. Since there's no n attached to that 3, we can just move it out of the summation. It's just a multiple. It's a scalar is another word to describe it. So I'm going to write it as 1 over n squared. Now, if I focus just on this series here, we should hopefully notice that right there is my p. And in this case, p equals 2. Since that is greater than 1, we know that this series will converge. Now again, I don't really care so much about what value it converges to, just that it does converge. That's the important part. By that logic, let's come over here and look at the other example. So the other example that I have starts at 2 instead of 1. Not a big deal here. It just changes what our starting value is. But it still goes to infinity, so that's the important part. Again, this is going to be an infinite series because we are going to infinity. And I'm going to rewrite that ever so slightly so that instead of having a square root of n in the bottom, I'm going to write it as a power, so it's n to the 1/2. Now, that means my p equals 1/2. Since that is less than or equal to 1, that tells me that this series should diverge. Okay, and that's going to be my final answer here. Now again, it doesn't really matter so much what this starting or initial value is, because again, we're going to infinity, and when we talk about converging and diverging, it's referring to end behavior, not so much what's happening at the beginning, okay? So we've done harmonic series, we've done P series. I'm going to talk about another one called telescoping series. Now, telescoping series don't have a formal way of writing the series at the beginning, but we'll notice with a telescoping series is more of a pattern. And so I'm going to go ahead and write down the pattern we're going to see. So with telescoping series, what we tend to see is that we're going to have a first term minus a second term, kind of like an alternating series. And then when I add to the next part, what I end up having is a repeat of the second number minus the third number. And then again, we'll add and we'll get the third number minus the fourth number. And then we'll add again and we'll get the fourth number minus the fifth number. And it keeps on going following this pattern. But so the key here about this telescoping series is you notice that I've got a negative and a positive of the same values. And so what ends up happening with this telescoping series is that they'll just kind of cancel each other out as we go along. Okay, so I want to go ahead and do a little bit of a proof with this. And so what I want to talk about for a moment is just kind of the concept of what's going to happen with this series. So let me approach it from the perspective of, I'm going to use the word partial sum. So I'm going to write it as S sub n. Instead of going all the way to infinity, we're just going to go out to the nth term. Okay, so what I'm going to do is I'm going to write this as a sub 1 minus a sub 2 plus a sub 2 minus a sub 3 plus a sub 3 minus a sub 4, and it keeps on going all the way out to the last thing should be a sub n minus a sub n plus 1. Or, yeah, minus a sub n plus 1. And so what we would notice is that all of these kind of middle numbers should cancel each other out. That's my simplifying phase. And even that a sub n should cancel out. And what I end up with left over is this minus a sub n plus 1. So if I were to do a partial sum, that's what I should simplify to get out. Is I should get a sub 1 minus a sub n plus 1. And so if I want to describe this infinite series, what I'm going to do is I'm going to find the limit as n goes to infinity of this a sub 1 minus a sub n plus 1. And so essentially all I'm trying to figure out is what's happening to this last little bitty term here at the end. And since this a sub 1 has nothing to do with n, what I can do is I can rewrite it as a sub 1 minus the limit as n goes to infinity of a sub n plus 1. So again, that's the second part of what I'll call the first term. And so what we'll notice here is that this telescoping series should converge to this value, so we can actually calculate what this is, so long as this limit exists, because that's the important part. And this actually refers back to the definition of convergence, is if this approaches some finite value, if this approaches something that I can actually figure out, then it's going to be convergent. However, if this limit does not exist, then we're going to have a divergent series. Typically what we'll find out with a lot of these telescoping ones, though, is that that limit goes to 0, because that's very helpful for us. We like when that happens. So let me go ahead and flip over and look at a couple of examples here. So these are some really nice, pretty examples of not necessarily convergent, but of telescoping series. I do want to point out that another thing that might happen here is sometimes these telescoping series are written as one fraction, and then by using that partial fraction decomposition that we learned about when we were doing the integrals, you can split it into two separate fractions that look something like this. So let me just kind of show you what happens, and we're going to start off with this n equals 1, and I'm going to just plug that in and show you where this goes. So the first one is going to be 1 over 4 times 1 is 4, minus 2 gives you 2. Minus, we'll plug in the 1, and so we'll do 4 times 1 is 4, plus 2 makes 6. So that's actually my first set of terms. Then we'll add the next one. So I'm going to plug in 2. So 4 times 2 is 8, minus 2 gives me the 6. And then 4 times 2 is 8 plus 2 gives me 10. And then I'll do the next one. So what we're going to see is that the next one is going to be, again, we're going to plug in 3. So we're going to do 4 times 3 minus 2. 4 times 3 is 12. Minus 2 gives me 10. And then we'll do 4 times 3 is 12. Plus 2 gives me 14. So again, notice that these terms are essentially canceling each other out as we go along. So the next one would end up being a plus 1/14. And then keeps on going like that. So what's happening here is we're saying that this pattern is going to kind of repeat itself. So I know that what's going to remain is this 1/2 minus the limit as n goes to infinity of, notice it's not going to be this first part, it's going to be this second part, the minus part, because again, the 1/6 came from this part first and then there. And then the 1/10 came from there, and then I canceled it out there. So again, this part is the one that's doing the canceling. This one's doing the canceling, and this one's going to be the leftover. Okay, and so what I'm going to do is I'm going to take the limit as n goes to infinity of 1 over 4n plus 2. I'm going to see what happens there. Now, what I'm going to do to just simplify this is I'm going to divide everything by n, and we'll see how that turns out nicely. Let's see. So if I divide everything by n, I get 1 over n divided by 4 plus 2 over n. And remember that when we take the limit as n goes to infinity, anything with an n in the bottom just goes to 0. I don't need to write the limit anymore. So I'm going to have 0 over 4 plus 0. Well, anything 0 divided by anything is just going to give me 0. So I'm going to have 1/2 minus 0, which is just 1/2. So this, in fact, does converge. And the cool thing about this, again, is we can actually find out its value. Again, not such a big deal all the time. Most of the time, we just want to make sure it converges. I did choose example 2 because it is a special case, and I wanted to show, again, the same reason here. So in this case, again, we are going to start off with n equals 1, so I'm going to plug in 1. 2 over 1 is 2. And then I'll plug in 1 over here, so we're going to do minus 2 over 1 plus 2, which gives me 2/3. Okay. Then I'll do the next one, so we'll plug in 2. 2 over 2 is 1. Minus 2 over 2 plus 2 is 4, so we're going to get 1/2 there. Now notice in this case right now, if I just do the first two terms, the first two, plugging in n values, I don't have anything that actually cancels out. So let's see what happens when I plug in 3. So 2 over 3, oh, there's my first cancellation, so I get 2/3. And then that's going to be minus 2/5. Let's keep going. So plus 1. So let's see, we're going to plug in, we just plugged in 3, we're going to plug in 4. So 2 over 4 is 1/2 plus 2 over, that should be minus, my apologies, minus 2 over 6, which is going to be 1/3 in this case. And so that's what's going to happen is, you notice there's the minus 2/3 and the plus 2/3, the minus 1/2 and the plus 1/2. So it's just taking it longer to start canceling out. And so I would expect the next one to be a 2/5. That would end up canceling. And so the reason I wanted, again, to show you this one is because notice, in this case, I don't just have one thing left over like when I had this other one where I just had the 1/2 left over at the beginning. In this case, what I have to start off with is I have to start off with a 2 and then a plus 1. And then I still have to, again, notice I'm still going to have this thing as the leftover. But I'm actually going to, if you notice, like I said, we're actually seeing it being left over twice. But I really don't have to worry about it the one time because, as you'll see, I'm going to write minus limit as n goes to infinity of 2 over n plus 2. So even if I do have it twice, we'll see what kind of happens here. So again, I'll kind of follow the same process. I'll divide everything by n, top and bottom. So the limit as n goes to infinity of 2 over n divided by 1 plus 2 over n. And remember, anything with an n in the bottom just turns into 0. So we end up getting minus 0 over 1 plus 0. Anything with a 0, it's going to be 2 plus 1 is 3 minus 0. So 3 is the answer. and that means it converges. So again, I didn't even have to write the repetitive term just because I know as the limit goes to n, as n goes to infinity, it's just going to be 0. So I don't have to worry about the fact that there's going to be 2 of them at the end, just that it's 0. So again, as long as I get a number out as the final answer, as long as this limit exists, it will converge. Now, the last 2 that I'm going to do are hopefully a little bit of a review for you. So the first one I'm going to talk about is Arithmetic Series. Again, the other one I'm going to talk about is Geometric Series. You've done both of those before. You should have done those when you were in Algebra 2, but this will be at least a nice review for us. So, Arithmetic Series are series that go from n equals 1, or you could start anywhere to infinity, and I'll write it as a sub 0, or whatever you want that first term to be, plus d times n minus 1. Now remember, d is called the common difference, and what this series is analogous to, it's similar to linear functions, okay? So essentially the d is the slope, okay? And we can call a sub 0, it's essentially the y-intercept. It's close enough to being what the y-intercept would be. And so what I'm going to do is I'm going to very briefly prove to you what happens with these. And so I'm going to start off with my arithmetic series as the summation of n equals 1 to infinity of a sub 0 plus d times n minus 1. And what I'm going to do is I'm going to take the limit of the sequence. So I'm going to find the limit as n goes to infinity of this a sub 0 plus d times n minus 1. And so the a sub 0 is just a constant. It's not going to matter so much. That d, again, is constant, not going to matter so much. What's going to happen, though, with this is as n goes to infinity, what we're going to see is that this whole sequence is either going to go to positive infinity if d is positive, and we'll see that it goes to negative infinity if d is negative. But either way, it's telling me that this limit does not exist. So that tells me that the arithmetic series always diverges. It always goes to either positive infinity or negative infinity by the nth term test. Because remember, with this nth term test, what it does is it says if the limit isn't 0, then I know it's going to diverge all the time. So let me go ahead and flip over and we'll talk about a couple of examples. Now, the first example I have right here should be a pretty easy one. It is the infinite series from n equals 1 to infinity of 9 plus 5 times n minus 1. Well, since this is an arithmetic series, we automatically know that this diverges. And that's all that I really care about. Again, I can't really find its value. It's not important. What's important is this diverges. Now, the next thing that I did want to mention is there is an arithmetic series partial sum formula that does come in handy a lot. Now, again, I'm calling it a partial sum formula because it finds the sum over a specific set of bounds. Like, for instance, in this case, I'm going to start at n equals 1 and I'm going to end at n equals 30. So I'm going to actually have, essentially about 30 different numbers in here. So there's 2 formulas for it. The first one basically just says if you know the first term and if you know the last term, you can figure out what the sum is there. The other one says if all you know is the first term, you can still figure it out, or if you know the common difference, that's also important for the second formula. But both of these formulas are pretty interchangeable. Since I actually have both of these, or I have all the information here, it's not particularly important which way that I do this. I'll probably just use the first one. So the y in this case is the 30. It's the ending place for my summation. So we'll do 30 minus x is the starting place, 1 plus 1. So again, y minus x plus 1, and we're going to divide that by 2. The other thing that I need to know is the first term and the last term, so all I'm going to do in order to do that is I'm going to actually plug in n equals 1 and see what happens, and I'm going to plug in n equals 30 and see what happens. So if I plug in 1, we're going to do 13 minus 4 times 1 minus 1, which should end up giving me 13. And if I plug in 30, we'll do 13 minus 4 times 30 minus 1, which I already did this earlier, should give me negative 103, okay? So I'm going to plug both of those in up here into my formula. And so we'll do the first term, which is the 13, plus the negative 103. And when I add those two things together, I should end up with negative 90. And if I do 30 minus 1 plus 1, I get 30 over 2, which will simplify to 15 times negative 90. And that gives me a total sum of negative 1350. I'm not going to really plug into this other blue formula. It should work out in the exact same answer no matter what. So I'm just going to leave that kind of up to you guys if you want to kind of test it out. But again, the answer you should get is negative 1350. Remember, important thing is that pretty much every partial sum is going to have a specific answer. We should be able to find it. It's the infinite series that we worry about more, like example 1. And this last one I'm going to do is the geometric series. Now, the definition for this I'm going to write down is very similar to ones we've done in the past. So it's n equals 1 to infinity, and I'll write a sub 0, which is my first term, times r to the n minus 1. Now, just like with arithmetic series, r has a special name. This is called the common ratio, and it is the base of the exponent. And so r could pretty much be any number we want. In this case, it could be positive, it could be negative. And this is analogous to, or very, very similar to, exponential functions. Whereas, again, arithmetic, we're close to linear functions. So these are close to exponential functions. I do have two formulas here for you that are very, very helpful. I am going to kind of prove both of them for you real quickly. The proof for them isn't particularly the most important part, but I do want to show them. So I'm going to start off with the partial sum formula, and I want to just kind of show you how that comes about. So I'm going to write, again, S sub n, which would represent the summation, and I'll write it as I equals 1 to n of a sub 0 times r to the I minus 1. And if I start off by plugging in 1, we get r to the 0, which is just 1, so we have a. I'm not even going to write the 0. I'm going to get rid of the 0. I don't really need the 0. So I'm just going to write a, and then if I plug in 2, we'll have a to the r to the 2 minus 1, which is just r to the first. So we're just going to keep repeatedly multiplying by r. So a to the r squared plus a times r cubed. And we're going to go all the way up to n, so I'm going to end up getting plus a to the r, or excuse me, a times r to the n minus 1. Because again, we're plugging in n right there. So n minus 1. Now, the next step in figuring out this partial sum formula is to multiply this partial sum we just got by r. And so that's going to give me ar squared plus ar cubed plus ar to the fourth plus dot, 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 all the way up to ar. And that's going to be another additional r, so it's going to be a times r to the n. What I'm going to do now is I'm going to subtract s sub n, so my first one, minus r times s sub n. So what you're going to notice here is that, and I'll try to do it in green, that if I subtract these, this is going to cancel, 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 and then it's going to cancel here. These are going to cancel, and I should just be left over with, as a final answer, the first term, which is a, plus a times r to the n. And I'm going to do two factorings. I'm going to factor out an s sub n on that first part. So we're going to do s sub n times 1 minus r. And I'll factor out an a on the other side. So we're going to have a times 1 plus r to the n. And then I'm just going to divide. So my partial sum gives me a times 1 plus r to the n over 1 minus r. Now, if you notice, all I did was change some of the symbols to get this formula up here. So again, this is my first term, and this is going to tell me how many things I'm adding up. So again, this formula and this formula are the same. In order to find the infinite sum formula, all I do is take the limit of that summation that we just found, that sum formula. So I'm going to write that as a times 1 plus r to the n over 1 minus r. Now again, most of this stuff doesn't have anything to do with n, so I can just move my limit to where it needs to be. So 1 plus the limit as n goes to infinity of r to the n over 1 minus r. Now, again, this is really important here to consider this fact that this is, again, technically an exponential function. So what we're going to see is that if r is bigger than 1, or even greater than or equal to 1, this is going to head toward infinity. So this is going to be a divergent limit. However, if r is less than 1, that is going to approach 0. So then the limit in this case is going to exist, and what we'll see is that we're going to do a times 1 plus 0, which is just 1 over 1 minus r. So if I simplify that ever so slightly, a times 1 is just a over 1 minus r. So this formula of using the first term divided by 1 minus that common ratio is only going to work when r is less than 1. And that's going to be an important fact for later on. So it's only going to converge when r is less than 1. However, if r is greater than or equal to 1, we've got a problem that's going to diverge. So let me go ahead and look at two examples. So both of these are infinite series. Oh, let me write down my result before I forget. So a geometric series will converge when r, the common ratio, is less than 1, and it will diverge when r is greater than or equal to 1. And this is linked to both exponential functions, but more importantly, to the definition of convergence, that limit has to exist in order for it to converge, okay? But so again, you might also want to remember that this is also linked to exponential functions in general. So let me go ahead and look at both of these sequences, or excuse me, these are series, and see what's happening here. So let's look at this first one. So with this first one, let's see. So my a sub 1, my first term is actually a 1. So if I were to plug in the number 1 here, we would get 2/3 to the 1 minus 1, which is 2/3 to the 0, which is just 1. So that's going to be my a sub x, my first term. And so in order to follow that formula, what I'm going to do is I'm going to take my 1 divided by 1 minus r, which in this case is 2/3. 1 minus 2/3 gives me 1/3. And anytime you divide by a fraction, you end up multiplying by the reciprocal. So my final answer is 3. Now, again, the good thing is, most of the time, I really don't care what that number is. I really care more about the fact that it converges. Again, the 3 is just kind of nice to have to know what the actual answer is. So again, this converges to the number 3, to the sum. For the last one, for example 2, again, we want to find what that first value is, so I'm going to plug in the number 1 here. So we're going to do 5 times negative 1/5 to the 1 minus 1. So that's going to turn into negative 1/5 to the 0. So we're multiplying 5 times 1, which is just 5. So my first term is the number 5 over 1 minus my common ratio, which is negative 1/5. Again, this is a formula that's specifically used for infinite sums, not partial sums. And so when I take 1 minus negative 1/5, that ends up being 1 plus 1/5, or 6/5. Now again, when we divide by a fraction, we are multiplying by its reciprocal, so I'm multiplying by 5/6. So my final answer here is 25 over 6. So even in this case, what we're seeing here is this negative, since it's less than 1, we're going to see that it also converges. And so I might just amend my my statement up here to include some absolute values, that as long as, my number is between negative 1 and positive 1, that it will converge. Anytime it's greater than or equal to 1, or even less than or equal to negative 1, it would also diverge. So it's important to consider, again, that what we're talking about is it could be a positive ratio or a negative ratio. As long as the number itself is less than 1, we're happy. Okay, so just to recap, we've talked about harmonic series, which is a special case of P series, which are analogous to P integrals. We talked about telescoping series, which are very similar to alternating series, and they cancel different parts out. We talked about arithmetic series, which are very close to linear, and geometric series, which are close to exponential. I hope this helped you guys out in better understanding these common types of series, because they're especially useful using the limit comparison test and the direct comparison test. They're also very helpful to know just because you can quickly identify some of the more common sequences in series that we deal with.